Recorded is rolling. It is Monday, May 5th. Cinco de Mayo. Got a Kahoot up ready to go. It's going to be exam review part two of three. So you guys got these study guides out ready to go. Because you guys know the final exam is going to be open notes, which includes the study guide page, 50 conceptual questions, 1 point each. We're going to straight up here. And then the second half is going to be 10 equation-based questions, 5 points apiece. I will provide you guys the equations. So you just have to know how to interpret them, how to plug the numbers in, how to do the algebra to solve. Okay, guys, good. Okay, now, my original plan, I think I told you guys last week, was I wanted to alternate back and forth between this and quantum journals, but tomorrow I actually have to proctor an AP exam, so that'll be during the afternoon. All my afternoon classes are getting relocated, and then my morning class, well, one's AP, so they got their own thing going on. So my non-relocated honors classes tomorrow. I'm just gonna have a study and makeup and board games day. I've got some books to you guys can read. But my afternoon classes, there's relocations. So guys, everybody here, looking at the screen right now. Everybody look up here. So are you guys gonna since you guys are right in front of me right now, or fifth period, are you guys coming to this class tomorrow? Oh, so you guys know where you're going. Is everybody good? What they're doing? All right, ready for Kahoot. It's gonna be Kahoot time. Oh, look at you guys, ready to go. You guys got study guides? Here we go. Yeah, here we go. First law of thermodynamics. Is a conservation of energy. Remember, you cannot create energy, you cannot destroy energy. If you think in terms of energy, you can do energy accounting. Energy is allowed to change form. You can change from potential to kinetic to, and the new one is thermal, right? So you guys remember delta Q can be MC delta T as long as the object stays within phase. All right, so conservation of energy. You guys good? All right, and points on the board. The greater the difference in temperature between input and output reservoir for a heat engine, this one right here about. Yeah, that would give you better efficiency. Maybe I should have made that one a few seconds longer. Okay, but let's look at this here. So here's the post you guys got. Do you guys remember I played you guys a Bill Nye video? He had one of these Stirling engines, where he put this on a cup of hot water and it started spinning. And actually, then he transferred it over to a glass of ice water and it would start spinning the other way. You guys remember that? But guys, what if you put it on room temperature water? And so the difference between the hot sink and the cold, because the other temperature was room temperature. Guys, what's the difference between room temperature and room temperature water? What's the temperature difference? Zero. No. And would this spin at all? No, it wouldn't spin at all. Here's your Carnot efficiency. Now, this is the maximum efficiency you can get from a heat engine. The actual efficiency is more like this formula down here. But let's look at the Carnot ideal efficiency. This is eta for efficiency. Right. 1 minus cold sink over hot sink temperatures. Now, guys, can you go plug in Celsius into here, or do you have to use what? Kelvin. These have to be absolute temperatures, right? Absolute temperatures. All right, so let's say you had, like 200 Kelvin here and 2000 Kelvin here. Guys, what is 200 over 2000? Is that 10%? Call it 0.1. Guys, what's 1 minus 0.1? 0.9, like 90%. So you can get like maybe 9% efficiency out of that, 90%. Okay. But guys, what about this? What if you have room temperature? What if you have about 300 Kelvin and about 300 Kelvin? What's 300 over 300? 1. What's 1 minus 1? 0. Ooh, that would be not spinning at all. All right, so you guys good with efficiency? Okay. I think you guys are going to calculate. Everybody's got a calculator, right? Calculator? I think one of these questions coming up has to do with the temperature. It's got Elise, Zariana, 2004. Zach, Alexander. Two identical blocks of iron, one's at 10 degrees Celsius, one's at 20 degrees Celsius, put in contact, closed system. Suppose the colder block cools down to 5 degrees and the warmer block warms up to 25 degrees. Now that's never going to happen because that would be a violation of Ah, look at you guys. You guys, yeah, second law of thermo. Right. Yeah, in terms of the first law, it's actually safe. In terms of the quantity of energy accounting, it's actually no problem there. But you guys remember the second law has something to do with the time order of spontaneous processes, right? Do you guys remember running a few entropy equations in here? Some in your notes, some of that thermo packet. You guys remember that thermo packet? Right. Now, guys, if you run the entropy equations, the change in entropy for spontaneous processes, entropy always does what as time moves forward? Increases. Yeah, is that some energy transfer over temperature? Right. So yeah, you could show that for that scenario, the reverse would happen, which would violate the second law of thermo, and so it would never happen. Right. Different ways to think about that. Right? They should reach an equilibrium temperature, not get more extreme. All right. All right, we got 7675447. Elise, Zariana, Zach, Alexander. Running a refrigerator with the door open in a hot room. Ah, I told you guys this question was coming. Yeah. All right. Oh, man. I think it's a good class to record. Because, wait, what about all the cold dumping out the front? Shouldn't that make the room colder? But don't forget, what's dumping out the back of the fridge? All the hot air, right? In fact, guys, is refrigeration a spontaneous process, or do you have to have the fridge plugged into the wall and drawing energy off the grid? Yeah, how about drawing energy off the grid? So overall, the hot's going to beat the cold. It's going to warm the house up. Yeah, yeah. All right. Do you guys remember the similar? You guys remember if you walk down an old part of town, all those air conditioning units are sticking out the windows? Yeah, because the condenser half of that system has to dump the hot air out into the atmosphere so it can make the room cold. Yeah. Yeah. Okay, so running the fridge, door open all day makes the room warmer. Warmer. Here you go, calculator time. What's the ideal efficiency? There's your hot and cold sink. 2050 Kelvin, 310 Kelvin. So try that. Do 1 minus 310 over 2050. Yeah, should be 85%. Here, do that with the guys. So I typed it. So I'm playing off this Cardinal ideal efficiency. Right. So 1 minus 310 Kelvin, 2050 Kelvin. And notice I gave them to you in Kelvin. Guys, what if suppose you see a similar question in college, but they give you Celsius? Guys, what do you have to do first? Can you plug Celsius in here? No. Do you have to add 273 to each one to get it in Kelvin first? Yeah, no, that's taken care of. What is this? 0.8487. Does that round to 0.85? Does that mean 85%? So you can get up to 85% efficiency with those two sinks right there. 85%. All right, we got Luciana, Peyton, Zariana, Zach, Alexander. Standing waves can be set up. Yeah. All right. Now, those are different categories of waves, like blowing across the top of a bottle or organ pipes. I think those would be more like longitudinal sound waves, pressure waves. Okay. Guitar string, I think, is more like a transverse wave. Okay. Okay. But they can be standing waves. So guitar string, you think you could have like nodal points at the end of the string and an antinode right in the middle. Boing, 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 boing. And these other types of waves, maybe you have high and low pressure points to just kind of hover sit. You guys remember doing that lab with the PVC pipe in the water? Right? Set up a standing wave, it would resonate. Okay. All right. Ooh, some good winners here. Suppose bugs jiggling up and down and swimming towards you at the same time. Compared to the frequency of the bugs emitting waves, the frequency of the waves reaching you. Ooh, ooh, higher frequency, right? And guys, what's the name of that effect? That's called the Doppler effect. Okay. Yeah, take another look at this. Okay. So I know the poster is showing a car driving through the air, and here's an observer. This sound like right, something like that. The car back. Okay. Now replace the car with the bug and the air with water, and now here's still the observer. Now the bug's swimming towards you. Right. Actually, how about this, guys? What if the bug's not swimming at all? What if the bug's just hopping up and down, and the water's also not moving? Would these be all concentric circles, just out like that? Right. And then maybe the bug's going blip, 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 and the wave crest reaching you is like blip, 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 and then someone on the side like blip, 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 and all the same, right? Now let's put the bug in motion. Now, are these still circles? Are they still circles? Yes, which means what about the speed? Is does the speed of the water ripples change? Yes or no? Yeah, speed stays the same. Because once that ripple wave's been released into the medium, it just goes at whatever speed it's going to go, right? How about this? What if I talk like this all day? What if I talk like this all class period? Are those sound waves traveling at the same speed? Yes, same speed. Just actually, I think I'm referring to a different. Actually, I'm referring to this one right here. Sorry about that. Right. So if I talk in the high pitch, or if I talk in the low pitch, change the frequency, but the speed's the same, but the wavelength is different, right? So I kind of overlist there, right? Because now if the bug's swimming towards you, do you think the bug might go on blip, 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 but these crests are reaching you more frequently? It's like blip, 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 and on the other side, it's like blip, 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 right? And there's the formula to tie all that together, right? Oh, this, guys, on the final exam, suppose I throw some numbers at you. What if I give you the car horn frequency, and I give you the speed of sound, probably about 340 some meters per second, and maybe the observer is just standing there, so that could go away. And I give you the speed of the car. Now, if the car's headed towards you, should you add or subtract down here? Subtract. And if the car's going away from you, should you add down here? Right. So you can get either a higher or lower observed frequency corresponding. If you're not sure, try them both out. Because if you subtract, you'll get a higher frequency. If you add, you get a lower frequency. That would match the stories. So you guys can navigate that. You see that on the final? All right, you guys go with the Doppler effect. Doppler. All right. All right. As the sound of a car's horn passes or recedes away from you, meow. There's Doppler. Yeah, decrease. There you go. You guys go with decrease. Okay. The pitch would decrease. Okay. Is there any question on that? If you guys had any questions, let me know. Got Luciana, Zariana, Zach, Peyton, Alexander. Child swings back and forth on a playground swing. If he stands rather than sits, what's the time period? If you stand rather than sit. Yeah, nice. All right. So pendulum physics. There you go. Pendulum physics. Okay. So the time to swing back and forth is this right here. Okay. Now, suppose the kid sit down. Here's the kid sit down. It takes some time to go back and forth. Okay. But guys, if the kid stands up, is he moving his center mass upward? And what's that? What's happening to the effective length of the pendulum? It's getting what? It's getting shorter. So length's getting shorter. Now let's take this over here. Guys, if the length's getting shorter, what's happening to the time period? It also gets shorter, doesn't it? So maybe the original kid sitting, it's like swing, swing. And the kid standing, it's like swing, 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 swing. Exaggerating a little bit. You guys get the idea? All right, shorter time. You also say a higher frequency if you wanted. Luciana, Peyton, Zariana, Zach, Alexander. Simple pendulum suspended in an elevator. When the elevator is accelerating upward, what happens to the time period? Yeah, would decrease. Ooh, still majority got that. Okay. Yeah, let's see why. Okay. So say I got this pendulum just out on the sidewalk. It's going swing, swing, swing. So okay, so that's our baseline. Right? Now let's take this into an elevator, and the elevator's accelerating upward. Because if you're standing on a scale, does that scale make it look like you're really heavy or really light? If you're accelerating upward, is it really being pushed into you? Really heavy? In fact, you feel really heavy, right? Feel really heavy? Okay. It's like somebody just turned up the gravity field. Might be really hard to tell the difference. If somebody turns up the gravity field, this G is getting really big. What's happening to the T? It's getting really small. So now this pendulum's going. Now, let's go the other way. You guys want to go the other way? What if you get into the elevator, somebody cuts the cable? Go into free fall. Guys, you're in free fall. What does it feel like the gravity field is? 0. You feel like an astronaut? What happens when you divide by 0? How much time would that take? Huh? What if it was, what if gravity field, guys, okay, what if gravity field was like 0.0001 meters per second squared? The time to swing back and forth would be very, very what? Very big? A lot of time? Here, let's do some numbers. 2 pi times the square root of, let's say the length is like 0.5 meters. Let's divide by 0.01 meters per second squared. So you're on some little tiny asteroid somewhere. How much time would it take to swing back and forth? It would take 44 seconds. Take 44 seconds. Ooh, that's a long time. What if you divide by 0? Do you get infinity or undefined? Right? In fact, I think this would happen. I think you pull the pendulum back, right? The elevator goes into free fall, and then you let this go. I don't think it swings at all. I think it just kind of hangs out there. It takes like infinity seconds to swing back and forth because it never swings back and forth. You guys get that? The pendulum in an elevator. All right, pretty good, pretty good. Points. Sound waves that has a higher frequency has a what kind of wavelength? Yeah, shorter wavelength. Right. That was the example I broke out a little bit earlier. Right. So am I talking a high voice? That's a high pitch. Talking a low voice. That's a low pitch. Changing the frequency. Is the speed the same? Speed's the same. Here, let's throw some numbers at this. Guys, what's the speed of sound approximately? Maybe 340, let's call it meters per second. Okay. What if I was talking at 340 hertz? Guys, 340 hertz. What would the wavelength be? Huh? 1 meter? Right? How about this? Guys, what if I double the pitch? Guys, if you double the pitch, is that like going up an octave? Double the pitch? Like at 680 hertz. 680 hertz. Now, does the speed stay the same? Speed's the same. That never changed. So what's the new wavelength? How about half of a meter? Right, you see it? Right. So there's an inverse relationship between wavelength and frequency. Dariana, Luciana, Peyton, Zach, Alexander. A leaf on a pond oscillates up and down 2 cycles per second. What's the frequency? What's that frequency? How about 2 hertz? Right. Now, here's a slightly different question. What's the time period between oscillations? 0.5 seconds. So the frequency is 2 hertz. The time period between crests, say, it would be half of a second, not hertz, but seconds, right? So that, okay? You guys got that? Well, but you're gonna get it a couple weeks. Yeah, we're gonna get it. Be fun. All right. Radio waves travel at the speed of light. Let's say the particular radio wave is 200 megahertz. What's the wavelength? Get this. Ooh, got some winners? Yeah. All right, let's check this out. So the version on the screen was c equals lambda f. This is more generally v equals lambda. So speed equals wavelength times frequency. Now let's do for light. Guys, what light has a special speed? Speed of light, I'll call c. Okay. So if I'm talking about electromagnetic waves, I might use that version. Okay. Now, say 300,000 kilometers per second. And then we're solving for wavelength. This is lambda right here. And the frequency was 200 megahertz. Okay. Now, before I run to the calculator, I want you to take care of these prefixes. Guys, kilo is a factor of a what? 1,000? Could that be? And then 300 million meters per second and base SI units. Okay. We're still solving for a wavelength. Lambda, wavelength. Okay. And guys, what's mega? Mega is a factor of a 1,000,000. So 200 million. That'd be hertz. Okay. Let's do one more thing. Why not? Can you put these on sort of scientific notation type? Okay. This is 3 times 10 to the 8 meters per second. Does that look definitely familiar from relativity? Because we use that all the time. Okay. Solve for wavelength. And I'm going to push this a little bit. I'll leave 200. Oh, yeah, instead of pure scientific notation is what I mean. Okay. Guys, mega, you said is 1,000,000. How many zeros is that? That's 10 to the power of what? Okay, yeah, it's true. It's pure scientific notation. It would be 2 times 10 to the 8. Right? But 200 mega. So like 6 zeros. So 1,000,000 6 zeros, right? Okay. Okay. Anyway, one way or another, divide down. I'm gonna get 1.5, and that'd be meters. Right. Can you take this and divide by this, or take this and divide by this? Okay, guys, do that. 3 over 2. It's 3 over 2. 3 over 2. You know what? Here, I got some trivia for you guys. Trivia. Okay. Does anybody listen to the radio? Anybody listen to the radio? Yeah, you guys change to the FM stations? Because the FM stations go from what to what? 87.5 to what's the highest you can go on the FM dial? It's like 107.9, right? So it is you can tune it to. That's a American radio thing. Right? Do these numbers have units attached to them? Because this is 87.5 what? Megahertz. And same thing here. Megahertz. Okay. So now you know when you tune it to an FM station, that's some number of megahertz is what that is. Now, Zariana, Luciana, Peyton, Zach, Alexander. Sound waves cannot travel in yeah, vacuum. There you go. Okay. In fact, you guys know what's the only type of wave that can travel through a vacuum? Yeah, electromagnetic radiation. Yeah, which includes light. So that could be a good answer too. Yeah, radiation. All right. And sound needs a medium to travel through because sound's a pressure wave. Okay. Elite. Oh, whoops. Sorry. Noise canceling headphones. Example of. Yeah, destructive interference. I got some demos for you guys earlier. They wanted to see some demo versions of this. All right, so here's your destructive interference. Now this is transverse waves. You guys know sound is longitudinal pressure waves, so a little different, but same idea, same principle. Okay. So when those pulses cross, see how they cancel out while they were crossing. Okay. Now if you replace those transverse pulses with high and low pressure, okay, you have some noise canceling headphones. It's an active process, maybe run by a battery, you flip it on. It reverses all the high and low pressure points, mixes it together, and you get zero sound going into your ears. Okay, here, I'll show you guys the constructive version of this. They want to see the constructive version. Let's go constructive. Oh, big wave. Constructive. All right, there you go. Destructive and constructive interference. Boom. All right, you guys good on that? Noise canceling headphones? All right, Elise, Peyton, Luciana, Alexander, Zach. Over 9,000. How far away is a jet plane? You hear a 2 second delay. Or how about lightning and thunder? You see the lightning, 2 seconds later, thunder. How far away? Here's your formula. Distance equals speed times time. Sound travels at 340 meters per second. Time delay is 2 seconds. Can you guys put that together right there? What's 340 times 2? Yeah, there you go. Right, so you guys can do distance equals speed times time. Right, so while you guys are writing that down, you guys have probably heard, here, if you see a lightning strike, suppose you count off 5 seconds before you hear the thunder, okay? Guys, if there's a 5 second delay, how many miles is that? That'd be one mile, right? 1 mile. So sound travels 1 mile every 5 seconds, okay? That's American units. Let's go to metric sort of. Guys, suppose you see lightning and you hear the thunder 3 seconds later. Guys, 3 seconds later. How many kilometers would that be? 1 kilometer, right? Because 1 kilometer turns out to be 3/5 of a mile, so pretty close, right? Right. Suppose you count off. What do I want to do here? 15 seconds. You see the lightning, you count 15 seconds. How many miles would that be? 3. How many kilometers would that be? 5. Yeah. Okay. So you guys can do distance equals speed times time. All right. Yeah. Oh, Tommy Chicho is back. Peyton, Luciana, Alexander, Zach. Which of the following is fundamentally different from the others? Fundamentally different. Ooh, right. Yes, those other ones, light waves, X-rays, radio waves, are all examples of what? Yeah, electromagnetic radiation. Right? Doesn't the blue, the green, and the yellow, don't those all travel at the speed of light through the vacuum of space? They could, right? But not sound. Guys, isn't sound a pressure wave, which is longitudinal, and it needs a medium to travel through? Also, it travels about 1,000,000 times slower than those other types. Okay. So the blue, the green, and the yellow are all kind of the same category. They're all EM waves, but the sound waves that's a different category. Okay, guys, good. All right. The main difference between a radio wave and a light wave. You guys go. Yeah, right. Because they all have the same speed, don't they? Okay, so they all travel at the speed of light. Yeah, they're all electromagnetic, traveling at the speed of light. Okay. So different wavelength works. Guys, what else could also have been a good answer? It's just not an option up there. They also have different what? Frequency. Aha. So wavelength works. Frequency would also work too. Okay. Right, guys, good. But they all have the same speed. Tommy Tito, Luciana, Peyton, Alexander, Jack. Main difference between a radio wave and a sound wave. Ooh. One winner. Yeah, basic nature. So guys, those are categorically different. Now, could you sort of compare wavelength and frequency and amplitude? Could be same, could be different. It's kind of apples and oranges because we're talking about 2 totally different categories of waves. Yeah, so the best answer is basic nature, okay? Categorization. Because you guys know radio waves are EM waves. You guys know sound waves are longitudinal pressure waves. Is everybody right? Compared to its speed in air, the speed of light in water is. Yeah, it's not as fast. It's a little slower. Okay. You guys remember this right here? Refraction. I got a couple of posters that go hand in hand. Refraction and Snell's law. Okay. So when light goes from air to water, or air to glass, or a vacuum to glass, it does slow down, and that kicks off this whole process that causes it to bend, which is called refraction. You guys remember that? Okay. So here, if you look at there's different ways to explain this. The way I think of it is all these wave crests. You guys see all these black lines of wave crests? Right? leaving the air is the same frequency as them leaving or entering the water. So the frequency stays the same. But the speed slows down, so the wavelength also gets smaller by the same proportion. That right now, how much does it slow down? Is related to something called the index of refraction. You guys remember this N right here? Is the index of refraction? Okay. So you got the speed of light in a vacuum, 3 times 10 to the 8 meters per second, and compared to the speed of light inside the particular medium. Does anybody know or remember? What is the index of refraction of water? So it's like 1.33, I think, 1.33, right? Or do you guys remember I gave you a little glass prism and a laser a few weeks ago? Guys, what's the index of refraction of that glass? Was pretty close to what? It's like 1.5, maybe 1.5, something like that. Okay. And for a perfect vacuum, it's exactly 1. It's C over C. And for air, it's pretty close to 1, so I usually just call it 1. It's like 1.001 or something like that. Okay. For air. All right, so you got index of refraction. Okay, so you guys good with that? With that? Yeah, Luciana, Peyton, Tommy Tutone, Alexander, Zach. Electron vibrates up and down 1,000 times per second. What's that called? 1,000 times per second. Yeah, frequency is 1,000 hertz. Frequency 1,000 hertz. Okay. Yeah, so you guys know the speed of any electromagnetic wave is always going to be 3 times 10 to the 8 meters per second. Here we got the frequency is 1,000 hertz. You could calculate the wavelength. Speed is wavelength is frequency. And time period. Guys, what would the time period be? Would it be 1 over 1,000 seconds? Yeah, maybe a millisecond, wouldn't it? All right, my winners here. 2 polarizing filters held at with their axes at right angles. How much light gets through? Zero. I'll show you guys that right here. Got some polarizing filters. Guys, suppose this was polarizing vertical and vertical. Is if I cross over vertical and vertical, does some light get through? Yeah, look at that. Plenty of light gets through. You guys can read all my Snell's Law poster back there, right? Vertical, vertical, right? But what if I turn one of these 90 degrees? Now, vertical versus horizontal, how much light's going to get through? No light. Ooh, look, it blocks it out. I can't read anything. Right? Ooh, look at that. Light. No light. Ooh, right. Now, when in your lives, I think I missed this a few weeks ago. Have you guys ever worn glasses where you have vertical on one eye and horizontal on the other eye? 3D glasses. 3D glasses. Okay. It's a little more complicated that they have some kind of spiral polarity, but the idea is to get different information to each eye. Yeah, so modern 3D glasses are polarizing. Yeah, they polarize differently. Okay. So you guys go to polarizing filters. All right, got Elise, Tommy Tuto, Peyton, Alexander, Zach. Colors on a TV screen, your phone screen. Yeah, color addition. Color addition. Right. Right. So how about this? Suppose you're an ant crawling around on your phone screen. You see a bunch of lights lighting up. You notice, hey, there's only 3 colors lighting up. Guess what are the only 3 color lights on your phone screen? Yeah, red, green, and blue. It's called the RGB standard. Red, green, and blue. Red, green, blue. Right. Guys, how about you as a human have what color detecting cones in your eyes? You only have 3. One for what, and what? Yeah, 1 red, 1 green, 1 blue. Yeah, and then your brain mixes and makes all the other colors from that you can perceive, right? How about your dog? Does your dog have the red one? No, Wolfie can't see red. Maybe that's probably about what your dog sees, right? Something like that. How about what else was I going to ask? Suppose all the lights are turned off on your phone. If nothing's lit up at all, what color is your phone? Black. Right. What if they're all lit up at the same time? What color does it make? White. What if there's no blue lit up, but it's all green and red? What color does it make? Yellow. Yellow. Great. Yellow, that's your phone screen. The more colors that light up, it adds together and it tends towards white. Okay, so that's additive mixing. All right. How about colors on a photograph or your ink printer? What's that? Yeah, color subtraction. Oh, everybody get it. Color subtraction. Okay. Uh, when you buy ink for your color printer, no, you can buy black ink it's by itself. But what about the colors? Guys, what are the only three colors you have besides the black? Yeah, yellow, magenta, cyan. What's that? I'm trying to remember the order they do that. Is it CMY, I think? Is it cyan, magenta? Anyways, it's these three. Okay. And because what if you run out of the pure black ink? Can you still get black? Yeah, by doing what? Yeah, run all three of these. And since it's subtractive, it subtracts all the wavelengths until it brings you to black. Aha, there you go. I got Elise, Tommy Two-Tone, Peyton, Alexander, Zach. The three color dots that make up color on a TV screen would be red, green, blue. RGB. RGB. Red, green, blue. All you need. The law of reflection. Law of reflection. All right. So another throw smaller. It says the angle of reflection matches the angle of incidence. Here's a bigger, better version of this. Okay. So you guys think that this light source is sending out like a billion rays of light all different directions? Okay. Here's a mirror. I have a vertically oriented mirror right here. Okay. I'm following one light ray. Okay. It's gonna bounce off that mirrored surface. Okay. Now, relative to this normal line, I can measure a couple of angles. I got this angle of incidence. I got this angle of reflection. Oh, I even have a protractor here. Look at this. Let's try this out. Okay. So measure what's this angle of incidence here? Looks like 31 degrees. What's this angle of reflection right here? It is also 31 degrees. Hey, 31 equals 31. So it's a match. There you go. All right, so you guys got law of reflection. Hey, what if I had a Kirby Funhouse mirror? Could I maybe create a bunch of normal lines all the way around and this would still apply? Yeah, law of reflection could still apply. Yeah, law of reflection. Person standing waist deep in a swimming pool appears to have short legs because of refraction. Refraction. All right, you guys go with refraction? Refraction. Elise, Tommy Two-Tone, Peyton, Alexander, Zach. The shortest plane mirror, you can see your entire image. The answer is right here. Do you see it, this little stick figure? How much mirror does this guy actually need to see his entire reflection? Half your height. Half your height. Here, I'll prove this to you guys. I'll prove it to you. All right, so let's get a floor going right here. Got a floor, a little half-inch floor. Okay. Let's get a big old dresser mirror. Big old dresser mirror. Big old dresser mirror right here. All right. You got a stick figure one side, and maybe sees this reflection about on the other side. Just about equidistant. Let's go. It's probably right back here. Boing. Get this, get this. I think its reflection would show up about here. About like that. Okay. Call this guy object. Call this guy image. And here's a mirror. Okay. However tall that guy is. Does he actually need the entire dresser mirror to see his reflection? No, he only needs some small part of it. Right. Now the catch is it needs to be positioned in just the right place. But how much mirror does he actually need? So let's see if from his eyeballs, what does his eyeballs see? So let's say his eyes are right back here. He's looking right at the mirror. He sees a light ray that looks like it came from this direction, which would represent the top of his head. But really, that light ray came from boing, this way right here. Is that true? Right. And does that follow the law of reflection? Now this is almost, but not quite horizontal. Do you think if that's 2 degrees, that's 2 degrees, maybe something like that? Right. He also looks down and he sees his feet in the mirror. So the feet of his reflection. Okay, it comes from that way right there. Okay. But really, that light ray came from boing, back that way right there. Is that also true? Yes? All right. So is everybody good with that? Okay. Now, who sees how much mirror does he actually need to see his entire reflection? Isn't it just this bit of mirror right here? That little bit? Right? And what do you think that mirror is compared to his height? Let's measure it. How tall is this guy? This guy is about 5.5 centimeters tall. About 5.5 centimeters. Let's check this out. It's about 2.75 centimeters. It's 2 3/4. Guys, what's 5.5 over 2? Whoops. 5.5 over 2. It's 2.75. Oh yeah. Physics wins again. Oh yeah. You guys got half your height. All right. Guys, try that. If you ever see a big reflective surface, I remember seeing this in an airport. It was night outside, big glass balls. Right. Stand close to the wall and then start back away from it. And look at where the top of your head is, where the bottom of your feet are in the reflection. And they don't actually change their position on that reflective surface. They stay same spot. Notice it didn't matter where I put the guy in front of the mirror. Could put him close or far away. Same answer. Okay. A rainbow nicely illustrates an example of. Okay, I'll walk you guys through it. Here's some white light. I see some refraction in this water droplet. I see some internal reflection. I see a second refraction. And here's an observer. So what do you need to make a rainbow work? Yeah, you need both. Okay, let's go through that one more time. Okay, so because when you see a rainbow in the sky, where is the sun relative to you in the rainbow? The sun is where? Blah, 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 blah. Behind you is the sun. Sending all this white light, right, all the colors, all the white light. Okay. Maybe you have billions of water droplets. Is that where you normally see a rainbow? It's all misty, post-rainstorm kind of in front of you. Okay. So here you got a couple of interacting raindrops. And so we got some refraction here, reflection, and refraction. Because different wavelengths of light refract slightly differently, right? The violet refracts more than the red does. Right? Then the colors spread out. Looks like a rainbow. Some numbers on there. Elise, Peyton, Alexander, Tommy Tutum, Zach. Chromatic aberration. Ooh. Okay. A couple of guys got it. Oh. Different color light rays refract at different angles if they pass through a lens. So different colors refract at a little bit different angles. Hey, isn't that the same thing as this rainbow over here? Hey, as you guys see, actually that happened twice. We got 2 refractions going on. And that would also be true for any lens. So the picture I had up here before it went away was some different types of telescopes. Suppose it's, like 1500, 1600, something. You're standing with Galileo. You got an old Galileo style telescope, an old pirate looking telescope, okay? Which works with lenses. Now it'll refract light. Suppose you're trying to look at Jupiter. Do you think that Jupiter looks maybe a little bit spread out because the because the violet end of the spectrum refracts more than the red does. So all right. That's called chromatic aberration. Right. Because what's the solution to that? Because modern day telescopes like the Hubble telescope, the James Webb, those actually you could replace one of the lenses with a what? With a mirror. With a mirror. Yeah. Yeah. Did I tell you guys who invented the reflecting telescope? It was who was that? Was that Newton? Isaac Newton? Yeah. So yeah. Because the mirror doesn't have that aberration to it. Oh, there you go. All right, we got. Oh, all right. You guys good? You're going to. You're going to where?
Oh, I was. All right, the bell's better.
Oh, is it?
Yeah.
Oh, dang. What? Oh, last one. Okay, last one right here. Magnifying glass will magnify. Oh, here. Here, guys. So this has to do with indices of refraction. So indices of refraction of air is 1, glass we'll call 1.5, water is 1.33. So underwater, it's not going to magnify as much. Okay, right? Because the difference in indices of refraction is really small. Okay, you get a greater difference from glass to air. Right. Right, so let's see who won. We got with the bronze, Tommy Cheecham, silver, Alexander, Zach with the gold. Oh, that. All right, nice job, guys. All right, some of my classes I'll see you tomorrow. Some will see you on Wednesday. Guys, make good use of tomorrow.